Hi guys, I would like to introduce this intermediate value theorem. And this theorem is useful to approximate some zeros or roots or solution of a equation. And I'll demonstrate that application in the problem below. So let's first read through the theorem, try to understand it and identify the key words in the theorem. So it says, suppose f is continuous. The book says f is a polynomial. I dislike that idea. We should not restrict f to be a polynomial. As long as f is continuous, this theorem will always work. So I don't like this idea to be restricted to polynomial. Now, so by the way, when we read, we should highlight, right? So continuous is important. On AB, okay, this is important. Take a look at this AB. It's brackets, so both ends brackets. That means including AB. So f is continuous from starting from A, ending at B. And L is the number between f of A and f of B. Okay, now let's take a look at this graph when we read the theorem. In this case, f is continuous from A starting at point A and ending at point B, right? Okay. Now, and L is any number in between f of A, which is this point, and f of B is this point. So L is any number in between. And then the conclusion says there is at least one number C in AB. Now, this we have to pay attention to this AB. If you compare this with the previous this interval, the previous interval is a closed interval, and this interval is open interval. So in other words, C is inside AB, not at the endpoints. There is at least one C in between AB, satisfying f of C equals L. Do you see that right here? Suppose this is L. Do you see that right here? C is in between AB. F of C equals L, right? So that's what this theorem is saying. So in other words, f takes on every value between f of A and f of B. For instance, this is f of A. This is f of A. The bottom one is f of A. The top one is f of B. Okay, now imagine, I'm going to zoom in a little here. So imagine any value in between f of A and f of B, any value here. So you pick another one, say this is another one. Do you see I can always find another C right here? F of C is equal to the value you pick, right? So that's what this theorem is all about. Okay, so let's first make sure that we understand the theorem, what theorem says. Now, let me zoom out a little bit here. Let's take a look at another graph. So this time, if you look at it, this is f of A, this is f of B, right? And this function is continuous starting at point A and ending at point B. Now, pick, say, this L value in between f of A and f of B. So the theorem says there is at least one, right? At least one. In previous example, there's only one C in this case. But here, when this L, for this L value, you see there are three different values in between A and B. So that the function value at these three x values, they're taking this L value. Okay. So that's what this intermediate value theorem says. Let's take a look at its application in this particular problem. So this problem, you're given a function, a polynomial function f of x, x cubed minus x squared plus 1. And without a graphing utility, you probably you know the end behavior. The end behavior like that, right? Looks like that. But you have no idea what's inside, okay, without using a graphing calculator. At this point, of course, you can if you go to calculus class, there are plenty of techniques that you can learn to graph this function. But at this point in time, without graphing calculator, we are not able to actually see it. Now we want to show that there is a 0 of f between -1 and 1 by showing f of -1 and f of 1 are opposite sign. Okay, there's a typo here of opposite signs. So first of all, first thing that I want to check is f of x is a polynomial, right? And being a polynomial, therefore it is continuous. It is continuous everywhere, including from -1 to 1. Okay, everywhere. Actually, this is everywhere. Everywhere. And why do I restrict this to -1 and 1? I just want to make sure that when you read the theorem, we match the assumption, the conditions. So this theorem says f is continuous. That's why I try to mention that it is continuous. Why it is continuous? Because it's a polynomial. Polynomial is continuous everywhere. And another requirement is continuous on this closed interval. So I'm gonna, because we're interested in there's a 0 between -1 and 1, so that's why I kind of focus on this interval. Again, it is continuous everywhere, but I just want to focus on this interval. Now second thing is this. Take a look at f of -1. What is f of -1? It is -1 cubed minus -1 squared plus 1, which is -1 minus 1 plus 1 if you do the algebra, which is -1, right? -1. Obviously, this -1 is less than 0. And then also I'm going to check f of 1. F of 1 means 1 cubed minus 1 squared plus 1. Again, what am I doing? I'm just substituting 1 into this polynomial function. So after the algebra, you know this is 1. And keep in mind, this is greater than 0. Now, according to the theorem here, it says L is the number between f of a and f of b. So L is the number between the function value at these two endpoints. Do you see that the function value at the left endpoint is -1 and at the right endpoint is 1, and 0 is the number in between -1 and 1. Okay, now the conclusion says there is at least one number in between this -1 and 1 satisfying f of this number is equal to L, which is 0 in this case. Therefore, which says, hey, there's a 0 of f between this -1 and 1 interval. Graphically speaking, this is what I would explain. So this is -1, this is 1. According to our algebra, f of -1 is equal to -1, right? So therefore, when x is -1, y is also -1. In other words, this point right here, -1 and 1 should be on the graph of this function. Similarly, when f of 1, the value is 1, and x is 1, the value is 1 right here. Okay. Now, because this function is actually continuous, so now because it's continuous, you're going to start at this point, and then it must across this axis at some point, right? Because it's continuous, connecting these two endpoints. So it must across this x-axis at some point. And this guy is actually the 0, okay? Where does it cross across the x-axis? You don't know it yet, but you just can be sure there is a point that will cross. So this is, therefore, here you can make a conclusion. Therefore, there is a 0 of f on the interval -1 to 1. Okay, where it is the 0, you don't know. Now, can you find it? you can try to approximate it, and here's how. Oh, by the way, this conclusion is just by the intermediate value theorem, right, from above. So this kind of finishes my lecture. However, if you I would like to do a little extension. Suppose you want to see, hey, I know there's a root in between, but where it is, you can narrow it down. This is what you can do. Okay, I'm gonna erase this. Oops, maybe I'll just create another graph. So when 1, this is 1, right? When -1, this is -1. So you know the function, this is positive, this is negative here. Now on -1 to 1, the midpoint, midpoint is this, midpoint, right? The midpoint is 0. So this is the midpoint, okay? Now check f of midpoint, okay? F of midpoint. So because which is f of 0, so plug in 0 into this function, you see f of 0 is actually equal to 1. So f of 0 is equal to 1, right? Okay. Now here's the interesting thing. You see at this 0, when this is 0, function is positive. Function is positive. F of -1 is negative. Therefore, and you know this function is continuous. Therefore, the 0 must be on this side. This side must be on must have a 0 because 1 is positive, 1 is negative, and this graph is continuous. It must across this somewhere, right? So with that, you know, hey, 0 is here. So next thing I'm gonna try the midpoint of this guy. So now I'm gonna look at the 0 must be in this interval. And I'm gonna try the midpoint, which is -1/2, and then you're gonna find the f of -1/2. In this case, it's gonna be, if you plug that in, 1/4 plus 1, which is actually less than 0. If you do the algebra, actually no, it's still greater than 0. I'm sorry that I should be a little more mindful in my algebra. Actually, this is greater than 0 if you do the algebra. So which means it is still here, somewhere above 0. And then you can conclude now, because this is positive, this is negative, the root, the 0 must be in between -1 to -1/2. Okay, you can just continue this process. Every step, you narrow it down to a smaller interval. Eventually, you will approximate these roots at any accuracy that you want. But that's not something we will do in this class, just for your information only.